Now let's study power of a lens. So whenever a parallel beam of ray passes through a lens, the ray either gets converged or gets diverged. That means if a ray of light passing through a lens gets converged to a greater extent or gets diverged to a greater extent, then the power of a lens will be more. So you can see the definition over here. Power of a lens is a measure of its degree of convergence or divergence of a given beam of ray. That means if a given beam of ray passes through a lens, how much convergence or divergence a given lens can produce for a given beam of ray. Or in other language you can say it is the ability of a lens to converge or to diverge a given beam of ray. That means if the power of a lens is more, the degree of divergence for a given beam of ray will be more, or the degree of convergence for a given beam of ray will be more. I can illustrate you this concept on a diagram, but one thing I would like to tell you that for a thicker lens, the focal length is very short. The focal length is very short, and for a thinner lens, the focal length is long. So can I say I have considered thick lens on a convex and a concave? So definitely for convex, the focal length will be very short. Let's say this is f2. So this will be the focal length f2, and for thin lens of convex type, the focal length will be long. So this is f2, and this entire length will be small f2, right? And for concave lens, it is a thick, so focal length will be short. So this is f2, and this distance will be called as second focal length, and since it is a thin lens, the focal length will be long. So this is f2. Now I have considered some parallel rays which are passing through the given lenses. So in the first case, the parallel ray passing through the lens will definitely pass through f2. So you can see the rays are converging at this point. When the same parallel rays, when passing through a thinner lens, these rays are converging at this point. So come on, tell me, in which case the convergence is more? In which case a ray of light traveling parallel to principal axis gets converged to a greater extent? You can see in the first figure, the ray gets converged to a greater extent because this angle is more. The degree of convergence is more. But in the second case, you can see the degree of convergence is less. That means a parallel beam of ray has to travel a longer distance to get converged, and here it has to travel a shorter distance to get converged. So here we can say the power of this lens is more and the power of this lens is less. If I talk about the second diagram, in case of concave lens, again parallel rays are traveling. So since this has a shorter focal length, we can say the rays get diverged like this, right? And in case of the second part, in case of thinner lens, the ray diverges like this. So a parallel beam of ray, you can say, sometimes diverges to a greater extent, sometimes diverges to a smaller extent. So in which case the divergence is more, we can see the divergence for this ray is more because this angle is more, and here the divergence is less. So from these two lenses, this lens produce more divergence. So in the first case, okay, in the first case, the thicker lens produce more convergence, and in the second case, the thicker lens produces more divergence. What we can conclude from this figure that the lens having shorter focal length, the convex lens having shorter focal length produces more convergence, whereas the concave lens having shorter focal length produces more divergence. That means shorter the focal length, greater is the measure of convergence or divergence, or greater is the degree of convergence or divergence. So from these examples we can say that power of a lens is somewhere inversely proportional. It is inversely proportional to the focal length. That means shorter the focal length, greater will be the degree of convergence or divergence. Greater the focal length, lesser will be degree of convergence or divergence.